You are welcome to ALB Next Gen STEM event. And we are so grateful to have you here. We're so happy to have you lovely people here. Today, we're going to be discussing a very, very wonderful subject matter, which is titled Exploring the Materials That Shape Our World. Now, if you're joining us for the first time, I would just like you to give us a wave. Yes, if you're joining us for the first time, give us a wave. And everyone, if you could just kindly type into the chat box where you're joining us from, that'll be lovely. Thank you very much. Thank you. Thanks for typing in. Yeah, welcome everyone who is joining us for the first time. We're very good. We're so happy to have you here. I'll start quickly by introducing AFBE UK. AFBE UK is a non-profit organization which started in 2007. And we have AFBE Scotland as well, which started in 2011. And we have our chairman, Dr. Olive Polion, who is also here, who has been leading this fantastic organization. AFBE UK, particularly Scotland, has 4 main streams. We've got the next gen. The next gen actually focuses on increasing STEM participation in primary and secondary school age children. And we organize STEM activities in schools through our STEM outreach program. We organize community outreaches as well as such as the one we're having just now. The second stream of AFBE is transition, and transition basically focuses on the university students, and what transition does is to introduce university students to the professional world, equipping them through the CV career and employability programs, and introducing them to the professional world through those programs, and helping them, acquire the necessary skills that they need to excel at work and as well as at their interviews. Another stream of AFBE UK is the real projects. So the real projects introduces university students to real life projects that are being carried out in the industries, equipping them with the right techniques for solving these problems in industries, so that when they meet these same problems at interviews or in real life at work, they become the solution providers that their companies want them or require them to be. The last but not the least stream of leadership program, and basically what the leadership program does is to help STEM professionals attain managerial and leadership levels within their companies through different leadership talks, through motivation, as well as mentoring program. Without further ado, I would like to introduce our speaker, Mo Oyetunji. Mo is currently a lead materials engineer at Baker Hughes, Aberdeen. She previously worked as a corrosions engineer at Cairn Offshore, Aberdeen. She holds a materials science and engineering honors degree from the University of Sheffield, and she also has an MSc in corrosion control engineering from the University of Manchester, UK. Mo is a professional member of the Institute of Materials, Minerals, and Mining. And she's also an active participant at the Institute of Corrosion Engineers. She's also a STEM ambassador and a co-coordinator of AFBE Next Gen.
Hi.
She is also the head of for African Affinity Forum at Baker Hughes, Aberdeen. She is passionate about and inspiring young people to be the best version of who they can ever be. So before I invite Mo to take over, I'll please ask that we mute our mics so that we can all hear Mo speak. And I'd also like us to kindly drop our questions into the chat box, and then your questions will be answered during the presentation or afterwards when Mo has finished giving her presentation. So it gives me great pleasure to welcome Mo Oyetunji to give her presentation. Mo, you are welcome.
Thank you very much, Rena. I appreciate it. Hi, everyone. You're welcome, everyone. I'm just going to share my screen, and if you're, depending on where you are, I'll say good morning, good afternoon, good evening, because I'm sure in Australia it's evening, just in case you're tuning in from there. I just want to tell you a little bit about myself. I'll put that on share screen. Can you all see my screen? If you can see my screen, just give me a wave. Can I? Yeah, awesome. Fantastic. So we'll be discussing, we'll be exploring the materials that shape our world today. And like Dr. Rena said, thank you for that introduction. If you have any questions, just drop it in the chat below. I'll tell you a little bit about myself. I know Rena has given a very robust introduction. My name is Lola Oyetunji. Some people call me Mo, some people call me Lola, depends on what you want to call me. I studied material science and engineering from the University of Sheffield in UK, and then went on. The picture on the right-hand side in orange is an overall where I worked at Shell, Nigeria as a maintenance engineer. I went to then further my studies in Manchester and found myself at Cannes in Aberdeen. I know that picture doesn't quite look like me right now, but it is me. And I am currently the lead materials engineer in Baker Hughes. A little fun fact about me, I love adventures. So anything adventures, I love doing. Now, what are we going to be talking about today? Today, we're going to be talking about material science engineering, what material science and engineering is. We're going to be talking about the classes of materials, the properties of materials, and I'm going to be doing a little demonstration for you, and we'll be looking at the careers in material science and engineering. Now, what is material science and engineering? Material science and engineering is an interdisciplinary field that uses physics, chemistry, and a little bit of biology. So you find elements of biology in material science and engineering. You can use it in different types of applications, from biotechnology to nanotechnology, manufacturing, corrosion, and many more places. So I'll just play this little video that will tell you a little bit about materials science and engineering.
Take a look around you. All the products that surround you in your home, school, or workplace are made of one material or another. We're surrounded by an incredible array of different materials every single day. Unless the thing you're looking at happens to be natural, like a tree or a flower, someone had to decide what material to make it from. Those people probably use some aspect of material science to make that choice. Materials science is a part of engineering that involves discovering and designing new materials and analyzing their properties and structure. That information can then be used to make design choices. We can also use our knowledge to break materials apart and recombine them in creative ways. For example, did you know that nylon is created from oil? That kind of thing wouldn't be possible without material science. Material science is important for the development of technology and has been for thousands of years. Different materials have different strengths and weaknesses and are better for different purposes. Since technology is the process of using our scientific knowledge to create devices and objects that benefit humans, understanding materials is an important step in this process. The more you understand the materials that you have to choose from, the better choices you will make. Materials studied in material science can be anything from simple materials like wood to modern man-made materials like plastic, to the very latest materials that involve nanotechnology and biotechnology. In fact, man-made materials are considered to be technology in and of themselves.
Awesome. So that is what material science is. And like they said in the video, it's important that you know the properties and structure of materials. That is how you actually choose how you make products and why you make certain products. So once you understand the properties of materials, once you understand the structure, you can then translate this to how you make your materials. So we'll look at the classification of materials.
Take a look around you.
Materials are classified into 4 major parts, okay? Now we have metals, ceramics, polymers, and composites. We'll start with metals. What are metals? So I'm sure everyone knows what metals are, okay? We'll start with this. So metals are materials like iron, steel, anything you can think of in your kitchen that is shiny, that is hard, that is strong, usually are metals. Now metals are divided into 3. You've got the ferrous metals, you've got non-ferrous metals, and you've got the metal alloys. Now, if we start with ferrous metals are anything that has iron, which is on the left-hand side of the periodic table. So I'm sure you can see metals over here. All metals are on the left-hand side of the periodic table. And ferrous metals, which is the first group under metals, has iron contained in it. Now, iron, it has a symbol on the periodic table known as Fe, and it has an atomic number of 26. So anything that has, any metal that has iron is a ferrous metal. So these types of metals will typically rust. So for example, if you put like this metal in your garden where it's moist, where you've got rain, where you've got oxygen, you would tend to see these things rust. And another fact about ferrous metals is that it's very, very corrosive. It's also magnetic. So ferrous metals, all ferrous metals are magnetic. Now the next type of metal is non-ferrous metal. So non-ferrous metals do not contain iron. And remember, the symbol for iron is Fe. So non-ferrous metals will not contain iron. They wouldn't rust when you put them in your garden or where you find water or where you find moisture. And an example of non-ferrous metals are things like aluminum, things like copper, things like nickel. So these metals do not generally rust when you put them where there's oxygen or moisture. And like I said, non-ferrous metals are non-magnetic. So these are non-ferrous metals. So like your canned Coke, usually made from aluminum, is non-magnetic. Things like your necklace that you wear, things like your earrings, most times they're non-ferrous. Now the third type is metal alloy. Metal alloys are a combination of 2 or more elements, as you can see on the periodic table right here, or a combination of 2 or more metallic elements. So for example, if you combine copper and tin, what would you get? You would get bronze. If you combine copper and zinc, you would get brass. And these are some examples of your metal alloys. So things like your saxophone, things like the ornaments around your house, most of them are all metal alloys because they have 2 combinations of metals. Now, the second class of material is ceramics. And ceramic is an interesting one. So a ceramic material is an organic, non-metallic material that is made from forming and sintering natural, so when I say natural, which is like sand, or synthetic materials at a very, very high temperature, okay? So I know I use the word sintering. Sintering is actually a process of compacting and forming a solid mass of materials by heat, or when you pressurize them, you pressurize them, but you don't quite melt them. You're heating it, but you're not quite melting them to liquefaction. So you're not making it liquid. It's still in the solid form, but you're taking it to high temperature to actually put them together and make them compact. Now, we have 2 types of ceramics. The first one's traditional ceramics, and the second one is advanced ceramics. So a quick one about traditional ceramics. Those ones are very easy. They are mainly clay-based, and you would typically see them all around your house. So like your pottery in your kitchen, like the ornaments and some things that your mom might put around the house to beautify the house. And you better not be breaking any of these because they're very, very, very brittle. Can easily be broken. And then moving on to advanced materials. Advanced materials actually consist of oxides, nitrides, silicides, borides, and carbides. A good example of that are your window panes, your glass. a lot of times, I'm sure most people, most glasses or most windows, you can see them, okay? And most glasses are made from silicon oxide, calcium carbonate, and a mixture of sodium carbonate. Now, these are a mixture of advanced materials that you can see, and they have excellent properties. They're really, really strong. They have a high hardness, and they're mainly corrosion resistant, meaning it would not rust. If you can see your glass or your window panes, you notice you can never see rust on them because they're corrosion resistant. Now, moving on to the second class of material, we have polymers. I love polymers very much. Polymers are materials that consist of large molecules or macromolecules. They're also containing long repeated chains of atoms in them. Now, monomers, I'll start with monomers. Monomers, can you hear me? Okay. Monomers is monomer is a molecule that can be bonded to other identical molecules to make a polymer. So mono, as you know, is one, and poly is actually multiple. So these multiple monomers connected to each other make a polymer. Now, there are three types of polymers. There's thermoplastic, thermosets, and elastomers. I'll just put this up here. Now, thermoplastics are linear polymers. Remember I said they're linked together to make a polymer. So monomers come together to make a polymer. Now, these thermoplastic have a straight, like a linear is more like a straight line. So these types of polymers are linear polymers. Thermoplastics can be melted easily. If you put them under heat, it would melt straight up. Hence why you can recycle it multiple times. So an example of that is plastic bottle. Acrylic can also be melted repeatedly. And you find these a lot of times around your house and you use them almost every day. The second type of polymer are thermosets. Now these ones are tricky. And I know you might disagree a bit, but these types of thermosets, once they are shaped, cannot be melted, except you go a really, really high temperature, but it's hard to do because that's why they're thermosets. Once you actually form them and you shape them, they cannot be melted. And an example of that are your tires. Hence why even when it's hot, you can actually go on the road for a very long time without your tires actually melting. Now, what would actually happen if your tires melt? That would be disastrous, wouldn't it? These types of polymers have branched polymers, as you can see, the very last one. So thermosets actually have branched polymers linking them together. Now, elastomers are the very last type of polymers, and these have cross-linked polymers. Polymers, these type of polymers do not have considerable irreversible extension. Now, for example, if I take my rubber band right now, I can stretch it and it still comes back. So they're usually reversible, okay? Now, a rubber band is a very good example of an elastomer. Going back, I forgot to do a test. Going back to metals, I'll go back to that. How you can test a metal is through a magnetic. If you get a magnet in your house, you can take the metal, and if it sticks, like I said, it's a ferrous metal. If it doesn't stick, it's a non-ferrous metal. Now, for example, my ring is made from platinum. And what is platinum? Platinum is a non-ferrous metal. So that's how you can actually test whether something's non-ferrous or ferrous. I'll move back to the end of polymers, which we have discussed. The very last class of material are composites. Now, composites are very, very hard to actually figure out or describe. Now, composites are materials that are made up of two or more of the different classes of materials. So you can have a composite that has polymer mixed with metal, or polymer mixed with ceramic, or ceramic mixed with metal. So a composite are essentially a composition of two or more materials mixed together. So you can do this by either layering two materials on top of each other, or by actually melting the materials and combining them together, literally mixing them up. Now, there are three types of composites, and you have metal matrix composites, polymer matrix composites, and you have ceramic matrix composites. Now, metal matrix composites, as the word means, have at least two constituents of these materials, and one being a metal. So these are typically high strength, high toughness, high stiffness, and high abrasion. A good example of this is a cermet. A cermet is a mixture of ceramic and metal, and these are used in dentistries for fillings. Now, if some of you want to be dentists, you'll be working with these type of metal matrix composites when you grow up. So better know your materials now. The next one would be polymers, polymer matrix composites. So these, like the name suggests, consist of one polymer in the combined material. And a lot of times you find resin as one of these materials in it. These are usually chosen because they're cheap, they're not as expensive, and it's really, really easy to make. So the fabrication process is quite easy. An example of this are your fiberglass. I'm sure you've all heard of fiberglass. Some bicycles are also made from polymer matrix composites. So you have your carbon fiber chairs, you have your carbon fiber bicycles, and these would be under polymer matrix composites. Now, the third one under composites are ceramic matrix composites. So ceramic matrix composites are ceramic fibers that are embedded in this matrix. So a mixture of materials, but that have ceramic in them. Now, these ones will be lightweight, they are hard, they are stable at high temperatures. And an example of this would be your bioceramics. Now, you would use this for hip replacements, and a lot of these composites are usually used in biotechnology or like in biomedical engineering. You usually find these composites used. Now, I'll take you back to my university. For my final year project, I actually use composites, and I call it a composites because I mixed materials to form a scaffold. So what we did was that we took a number of polymers, mixed it and electrospun it with some biodegradable substance, and we electrospun them into a conduit used for nerve regeneration. So these polymers were electrospun, and they were like a nerve. You know how your nerve looks? It's like a strip, very little. And you're able to insert these when your nerve breaks, and after a while you make it biocompatible, so you're putting some stem cells in them, and after a while they degrade. A lot of composites are used even for if you go to the hospital and you get like a stitch, the stitch are actually made from composites, and that's why after a while it degrades and you never even really see the stitch anymore. And that's the last class of materials. We are then going to be guessing what the material class is. I have 6 objects here, and please feel free to use the chat if you care to type in what your thoughts are. Now, I have 6 objects here, and I'm going to be asking you to guess the material. So the first material is, who knows what the first material is? Does anybody know? I'm guessing you're typing in the chat. The first material is the Louvre, and that is in Paris. And the Louvre Pyramid is made from glass. Well done, Daniel. And what is glass under, if you remember? Glass is under ceramic. Now, number 2, can anybody guess what number 2 is? Has anybody ever seen this before? Does anybody know where this is? This second object is?
Number 2.
Nobody knows. Nobody has actually typed it. Okay, so number 2 is a plastic bottle village, and that is in Panama. It's very interesting because this house you're seeing over here is actually made from plastic bottles. So essentially what they do is that they put sand, which is largely silicon oxide, and they use that to construct the house. it's interesting. When I saw it, I was like, oh, wow. And it was actually an architect. You can Google him. His name is Robert Benzo. He's actually a Canadian-born environmentalist who decided to clean up the water, and all these plastics he found, he actually used it to make these houses. It's in Panama. It's a bunch of houses known as Plastic Bottle Village. So these are made from composites. Now, the third one, does anybody have any idea what where the third building is? Anyone? I'll give you a clue. It's in Spain. Someone said Oslo. No, it's not Oslo. It's in Spain. It's a museum. It's not in Portugal. That building is in Spain, and it's a museum called the Guggenheim Museum. And awesome. Come the Tiger. Very interesting name. Well done. That is the Guggenheim Museum in Spain, and it is made from titanium. Does anybody know the class of material titanium falls under? Well done. Titanium falls under metal. Now, I know I've shown you the answer of the next one. Just a little fact about the museum. Exactly 442,875 titanium panels were used to make up this museum, designed by another Canadian-American architect called Frank Gehry. Okay, now what we have here are your dental fillings. Fantastic. So I'm sure most people here, if you've not visited the dentist, well done. It means you're controlling the amount of sweet intakes you're having. But if you go to the dentist, these are the type of fillings you would get. So you would get either the ones on the left or the ones on the right. And the ones on the left are made from a resin. And what did I say a resin are? Come the Tiger. A resin is made from composites. So the left one is a resin composite filling, which is a composite, and the right one are silver fillings. A lot of times people use the resin one because it's actually transparent, and that is what resin actually does. It mimics the color of your teeth, so you won't really notice you have a filling. So like I said, that is either composites, which is the resin filling, or the metal, which is the silver filling. Now, moving on to this bicycle. It's an interesting bicycle. Wouldn't we all agree? This bicycle is a carbon fiber bicycle. Now, can anyone tell me what class of material this bicycle will fall under? This bicycle, carbon fiber. Well done, Achibola. The carbon fiber bicycle would fall under composites. Well done. The very last one we have here is your mobile phone. I'm sure most people would have seen a mobile phone, except you're living in the cave. Everyone has a mobile phone. And what would you say this class of material falls under?
Metal.
It falls under metal. There's also polymer in here.
Excuse me, Auntie, going back to the fourth one, there's a little bit of that there.
What's that? Okay.
The
fourth one. Yeah, there's a little bit of that there.
If you have any questions, can you just put it into the chat? Okay? And I'll answer it. Urena will be able to help me collate the questions, and I would answer the questions. Now we have the material, we have the mobile phone, and your mobile phone has a little bit of everything. Well done, Cam the Tiger. So it has your metal, which is the aluminum alloy, which is the body. We choose aluminum because it's very light. So most of your phones, your iPhones or your Samsung phones would use aluminiums to choose them, which are metals. You also have lithium to use to make the batteries. Well done, Bolu, fantastic, which is what I was about to say. You also have lithium to use to make the batteries, and you have polymers to make them resistant to damage. And if you look on your screen, sometimes they're made from either ceramic, which are your screen, or polymers, which are plastic, that will make them resistant to damage. Well done for those who said lithium batteries. That's a very important component, because if you don't have those, it's very hard for your mobile phones to actually function. Now we move on to properties of materials. Materials have loads of properties. And when I say loads of properties, they're chemical properties, they're physical properties, they're mechanical properties, and they're dimensional properties. So
You want to start growing tomorrow.
From the size to the composition, to the density, to the corrosion property, you have all of these properties for any material you choose. Now we're going to be looking at the mechanical properties today, and we're going to be taking 3 groups of properties. So we're going to be looking at strength, we're going to be looking at elasticity and plasticity, and we're going to be looking at ductility and brittleness. So these are the properties we're going to be concentrating on today, just because we don't have that much time. Now let's start with strength. What is strength of a material? A strength of a material is the amount of force that is needed to break a material, usually by pushing, by pulling, or by sliding. Now I say these 3 because if you look on the right-hand side of the slide, tensile force is used to break a material by stretching the material and pulling it out. Compressive force is used to break a material by pushing it in. When you put stress on something from this side and you're pushing it in, that's compression. Or shear stress, when you actually shear something. So they're going in opposite planes, as you can see on the right-hand side. Now, stress is actually defined as the internal force per unit area. And I said internal force per unit area because it's not acting from the outside of the material. It's actually acting from the inside, which is stress. And mathematically, we can write that as force over area. So that stress is force over area. The unit of this is Pascal, which is the same as pressure, but it's not quite pressure. So both pressure are forces over area. So that is your strength of a material. So that force is what is required to break a material. That is how you actually quantify the strength of a material. Now we move over to the next property, which is elasticity and plasticity. Now, when a force, like I said, is applied to a surface of any material, the material goes through a physical change or deformation. Now that deformation is what we call a strain. So a strain is the deformation or the displacement of an object that an object undergoes due to an applied stress. And mathematically, we can write that as strain would be equal to the change of length over the original length. And that E you can find over there is called epsilon. Okay? Now, elasticity is defined as the property which enables the material to get back to recover its original shape. And remember when I brought back my elastic band, this has an elastic property, as you can see, because I'm stretching it, but it's coming back to the original shape. And this is a good example. Now, plasticity, on the other hand, is defined as the property which enables the material to be deformed continuously. So if you look on the right-hand side of the curve, it's going to go to the elastic behavior, and it's going to show that get to the plastic behavior. So it's going to continuously deform and not rupture until it gets to a particular amount of strain. So that is usually a permanent process. So it doesn't come back like the elastic material. That's what elasticity is. Elasticity is the material getting back to its original shape. Now, once a material undergoes plasticity, it's very hard for it to come back. That's why it's a permanent process. Now that is elasticity and that is plasticity. Now moving on to our last type of property, we have ductility and brittleness. Now what is a ductile material and what is a brittle material? There's a little video here showing what a ductile material is and a brittle material, but I'll just explain each of them. Now, a ductile material would undergo a significant plastic deformation under tensile stress before it ruptures. It can be bent, it can be stretched, and it can deform before fracture. It absorbs quite a lot of energy before it actually breaks, which I'll explain in my next slide. Now, a brittle material, on the other hand, has no significant deformation under tensile stress before it ruptures. So for example, your glass, when you drop it, what happens? It shatters, doesn't it? It's a very, very brittle material. It suddenly fails, it doesn't warn you before it breaks, and it tends to keep their shape until it fractures. And this type of material would absorb very little energy before it breaks. Now, I'll show you this little video, very short video, to describe a brittle material and a ductile material.
What would happen if you hit a piece of glass with a hammer? It would probably shatter into many pieces. What if you hit a piece of metal with a hammer instead? You would probably dent the metal, but it's unlikely that you would be able to break it. Why does the glass break and the metal only dent? Because glass is very brittle, whereas metal is not. We've all seen examples of metal being bent without breaking. You may crush a can before recycling it, dent your car in a fender bender, or even bend a metal wire to make your own jewelry. In all of these cases, the metal bends but does not break. This occurs because metal tends to be ductile. Ductility is a measure of how much a material can be deformed before breaking. Deformation occurs when a material's shape changes. A few examples of deformation are bending, stretching, and denting. Materials that can be deformed significantly before breaking are called ductile materials. Some examples of ductile materials are many metals and plastics. The opposite of ductile is brittle. Brittle materials don't deform much before breaking. Instead, they keep their shape right until they break. When brittle materials break, the cracks spread very rapidly, like in the case of shattering glass. Some examples of brittle materials are glasses and ceramics. When designing parts, engineers usually prefer ductile materials over brittle materials. One reason is that materials that undergo brittle fracture tend to fail catastrophically with little or no warning. A brittle pipe might appear to work perfectly one minute, but the next minute it could shatter and spew all of its contents. Ductile materials, on the other hand, tend to give visible warning signs before failing. A failing pipe that undergoes ductile fracture might have a bulge, dent, or small leak that grows for years before failing. Engineers can therefore monitor parts for visible changes and replace damaged parts before they fail. Ductile materials also tend to be more resilient to damage. If a car were made entirely of a brittle material like glass, a simple fender bender could shatter the entire car. Therefore, cars are generally made from more ductile materials, like metals, that can withstand fender benders without breaking. Ductility is a measure of how much a material can be deformed before it breaks. Ductile materials, like many metals and plastics, can be significantly bent, dented, stretched, or deformed in some way before they break. Brittle materials, like glasses and ceramics, are the opposite. They tend to keep their shape right up to the point they suddenly fracture. Ductile fracture is generally preferred to brittle fracture, since brittle materials tend to fail catastrophically with little warning.
Now that's it for now. I hope you all know the difference between a ductile material and a brittle material. So just before we go into our presentation, if you have any questions, please put it down in the chat. And as I said, Dr. Rena would be collating it at the end of the session for me to answer. Now we're just going to go to our little presentation, but before we do, this is the stress and strain curve of a ductile material and a brittle material. So like I said, a brittle material would absorb very little energy. The amount of the area here underneath the curve is the amount of energy that is absorbed by the material. Now, if you can see, the brittle material is absorbing very little energy, while the ductile material is absorbing a lot more energy before it breaks. And as you can also see, the plastic material, the ductile material, takes a while to deform. It goes up, and instead of it breaking at this point, it's still getting deformed. At this point, it's a permanent deformation, and it keeps going up until it breaks at this point. Now, if you look at the right-hand side of your slide, these are examples of how a ductile material, a semi-ductile break, and a brittle material would break. Now, the ductile break, as I mentioned earlier, would give you warning, hence why it takes a while to break. So it's like it's stretching before it breaks. If you look on the right-hand side, the brittle break is very sharp. So there's no warning. It's a sudden failure. It's literally breaking a biscuit, and that's going to be a brittle fracture. Now, the semi-ductile break, which is in the middle, would be known as a very low ductile material. So it would not be quite a ductile material and not quite a brittle material. So it's a semi-ductile material, and that's how the semi-ductile break looks. Now, going over to our little demonstration where we're going to be using a Kit Kat and Twix to describe what a brittle material looks like and a ductile material looks like. So that's my Twix over here. And don't worry, I'm not going to eat it. Orena, if you can kindly share my screen. I don't know if you can kindly spotlight my screen. I'm not sure if you can see my screen over here. Can everyone see it?
Yes.
Okay. So we're going to be demonstrating how the Kit Kat is going to break and how the Twix is going to break. Okay, so I have my knife over here. And that's how I'm going to apply the force. So remember, what did I say stress was? Stress was force over area. So this is the force, and this is the area where I'm going to be applying this force. So I'm going to be putting stress here to see how this is going to break. Okay, so I'm going to try once.
We can't see what you're doing.
Can you not see what I'm doing?
No, we can't.
No, we cannot.
Oh, I'm sorry about that.
Hold on a bit.
I will just. There's another screen called AFB, Next Gen AFB Scotland. If you pin that to your screen, I'm sure most of you would see that now.
Can you see that screen now?
That one?
Yeah, I'm watching it now.
Oh, yeah, we can
Are
see
you
it
there
now.
now?
Can you see it now?
That's good.
Yeah.
Awesome. Now, the Kit Kat, like I said, is what we're going to be doing first to see what type of material this demonstrates. And this is my knife. This is going to be my force over the area. So I'm going to be applying stress on here. And I'm going to do it multiple times just to show how long it would take to break. So I'm going to do that. And another one eventually broke. Now, if you look, based on what we were discussing, how does the break look like? Is it sharp or is it quite pointy? If you type in the chat to let me know what you think. Is this a brittle material or is it a ductile material? Can anybody see? It's a brittle material because it broke really sharp, didn't it?
Well done, Ose.
Okay, well done. Now I'm going to put that on the side and we're going to be looking at the Twix. Never seen a Twix white until today. Now the Twix one's a little bit smaller, so we're going to be making the bar a lot closer. Now we're going to be applying stress to this material. And remember, stress was force over area. So I'm going to be doing that. Did you see how that broke? Did it break really quickly? It broke quickly, but it took a while to break. And if you can see, can you see? Is this a ductile or a brittle material? It's a ductile material. Well done. So your Twix, your Kit Kat was your brittle material and your Twix was your ductile material. Now, let's look at Monomers. Monomers are another material, and I'm just going to use a green one, but I'm going to take it out. And we would describe what this is. I'll put this bar a little bit closer Although, as you can tell, it's not going to be as strong as the other two materials. So even when I just put this here, you would see that it doesn't take that much. As you can see, it's already bending. So it's a plastic material, okay? As you can see. So what I'm going to do is I'm going to stretch it. And I want you to explain to me what your thoughts are on this stretch. Is it increasing in length or decreasing? Can you all see it? It's increasing in length and it's going. And what happens? It breaks. Now at this point, it's super ductile. Well done. And remember when I explained strain, what did I say strain was? Strain is the change of length over the original length. So it's increasing in length. And if you notice, this was the length of the original. I don't know if you can see. This was the length of the original. And as you experience strain. So the change of length over this original length is what you know as the strain. And as you rightly guessed, your moms are plastic materials. Well done. I hope you enjoyed that presentation. I'm just going to stop my video and get back onto this. Right. Now, we are going to be doing a materials treasure hunt. I'm sure everyone loves a treasure hunt because I do. And we're going to be doing this in 3 minutes. We're going to be as quick as possible. There's going to be a timer on the screen. And what you're supposed to do is you're supposed to look for all 12 materials in your house under 3 minutes. Now, it's 1 person per household. Once you have all 12 materials, put it right beside you. You can either take a picture or you can count how many you have. Once you have 12, you type it in the chat, 12. Now the winner gets a prize at the end of the session, which I'll be announcing. So the aim is to get 12 materials in 3 minutes or even quicker. And based on the chat and based on what you type on the chat, that is how we'll choose the winner.
What did I miss?
I'm sorry?
What did I miss?
If you just watch the video, there's a video on here. You watch the video to know the materials, and you have 3 minutes to get all the materials, and we'll pick the winner. So once you get the materials, immediately you get all 12 materials, come back to the chat and you type 12. So you don't need to list all the materials you've got. You just type 12. Or if you've got 11, you type 11. If you've got 10, you type 10. Remember, mommies and daddies, you're not allowed to participate. This is only for the kids, okay? So 9 to 16-year-olds, you're allowed to participate. The winner gets a prize at the end of the session. all done? Are we all back? I hope we are, because 3 minutes is up. Yeah?
Yes.
So, Dr. Urena, can you help in collating the very first person? Did anybody get 12 materials? Let's start with that.
Yes, we actually had people who got 12 materials.
Wow, interesting.
Yeah.
We're going to visit that. So no cheating. So Dr. Urena, if you tell us who the first person was.
Yeah, so I'm going to call out the first person. And as I said in the chat box there, prepare to show us all 12 materials. So the first person is Nicholas.
Okay.
Nicholas had 12.
Okay.
And then we have Jude. Jude also had 12.
Okay.
And then we have Tabo. Tabo, who had 11, because Daniel said he had 12, but later on said he had 10. So
okay.
We've canceled out, yeah, so.
So the first person who got 12, was it, who got 12? The very first person?
Nicholas.
Nicholas. So can you tell us, can you nicely show us?
I think I got.
I'm so sorry, just hold on a bit.
7 or 8. I got either 7 or 8.
Oh, you got 8.
I got either 7 or 8.
No.
Okay. Is that Nicholas speaking?
Yeah. No, I'm
speaking
speaking now. Wait.
Okay, so Nicholas is speaking now. How many items did you get, Nicholas?
I got 11 or 12.
You got 11 or 12. Do you want to quickly count it?
Yeah. I'm done. Yeah, I got 11.
You got 11. Okay. Now, who is the next person who got 12?
So the next person is Jude.
Jude. So Jude, are you sure you got 12?
Is Jude still on the line?
Is Jude still on there? Quickly.
Jude,
Yeah.
unmute yourself and speak, yes?
Are you sure you got 12?
Yeah, I did get 12, but then I realized that there was a list. So after I ran and I got a mug, cutlery, CDs, yeah, I think that's all. But
So you got all 12. Did you get a racket?
No, I got 12 and then I found out there was a list, so I had to get more after that.
Okay.
All right. Okay. So we just thank you, Jude, for that.
Thank you very much, Jude.
Honest.
What about the next person?
So the next person here is Ayosku. Ayosku, are you there? If you could just unmute yourself and speak.
Yeah, I'm here.
Did
Okay.
you get 12?
I either got 9 or 10.
Oh no. So nobody got 12.
But someone got 11.
I got 11.
Who got 11? What's your name?
Nicholas had 11.
Yeah.
Nicholas. So Nicholas will be our winner for today. Now just going through the list because our time is fast spent on the classes of materials. So a cutlery is a metal, a CD is a polymer. Does anybody know what a canned drink is? What classification of material that is? Does anybody know?
A metal.
It's a metal. Can anybody guess? So I'm just going to do it at random. Can anybody guess what a racket is? What class? Sorry?
Plastic.
Plastic.
Not quite. Anybody else want to guess? What's a racket made from? What class of material?
Composite.
Well done. A racket is made from composites because it has a mix of different things in it. Remember what I said, you can mix the materials, you can layer them, you can actually melt them. So a racket is a good composite. A last one, a notebook. Does anybody know what a notebook is?
Polymer.
It's a composite as well.
A notebook is a composite. Well done.
Yeah.
A notebook is a composite because it's made from, I know some people might say a notebook is made from wood, but it's actually mixed with different materials to make it paper or to make a notebook, okay? So it's mixed with different materials. And one thing about polymers, I know I didn't mention it, but I'll just quickly touch on it. A polymers can actually be man-made or natural. Now, if you cut the bark of a tree, right, you would see a milkish liquid, and that milkish liquid is called pectin. That is a natural polymer. You also have man-made polymer, like your tires and like your rubber bands and, you know, all of those things. Those are synthetic polymers, right? So polymers can also be classed under man-made types of polymers and natural types of polymers. So time is fast spent. Just do a quick one. The last thing we're going to be talking about are careers in material science and engineering. If you study material science and engineering, and I hope some of you do, because I already saw in the chat, some people want to be engineers. You can either work in the oil and gas sector, you can work in advanced manufacturing, you can work in biotechnology, you can work in aerospace, you can work in communications, you can even work in research and development. So you can be one of those people that will make innovative materials and innovative products that we don't even know about or we can't even think about. So you can work in any one of these sectors as a material scientist and engineer. And going on to our next slide, these are some of the jobs where your degree would be useful. You can work as a biomedical engineer, you can work as a geotechnical engineer, you can even work as a patent examiner. So when people make materials, you can decide this is going to be our own, for whatever company you work for, you can decide this is going to be our own patent, and you can put a clause on it that if anyone else produces it, that's also under innovation. You can review it and know the type of material so that if anyone makes it, then you can sue them. You can also be a secondary school teacher. And these are on the right-hand side of the slide. These are the types of work that you can go into when you study material science and engineering. So these are some of the resources for learning. If you want to learn more about material science and engineering, you have the materials book by Sally Hewitt. That's really, really good. You also have study.com. I got some of the videos from study.com, which is really good and descriptive. You also have Club Site Kids. That has a lot of experiments for materials. You can quickly take a picture just to, you know, go on there. You also have the STEM learning. There are loads of activities and things to do on stem.org.uk. And that is it. So this is a homework for you guys. So you can use materials to make your own face shield. And if you just take a quick picture, we're not going to make a face shield here, but it's from my work. They actually advise us you can actually make your own face shield yourself, right? So these are the supplies you need. You need an elastic cord, a sponge. I'm sure you all have sponges at home. Some of you already help your parents wash plates at this age by now. You also need a hole puncher, you need a double-sided tape, you need a ruler, you need a plastic film, large enough to cover your face, you need scissors, a pair of scissors, and you also need stickers just to make it decorative. So if you get all these supplies, you can do your own DIY face shield. And these are the steps on how to make it. So if you want to take a quick picture of this slide and this step, or if you want to take a screenshot if you're using your phone, just so you can go home and make your own face shield. So you don't need to actually buy these things one at a time. So you can have multiple. If you just buy these items, you can always make a face shield. You can make one for your mom, you can make one for your dad, you can make one for your siblings. So this is the DIY face shield. So I'm guessing if you want to actually make it, just take a screenshot of it and you can do it in your own time. All right. And that's it. Congratulations to our scavenger hunt. If you send your name, your email to info@afb.org, you would get an Amazon voucher and also new supplies to make your own face shield. So we've got the acrylic here, we've got the sponge, we've got the double-sided tape. So I'll be posting that to you in your house. So if you send an email to info@afb.org, info@afbscotland.org with your name, your email to get your Amazon voucher, we will be sending that shortly. Thank you for listening. I hope you had a great time. And now we can take questions.
Thank you so much, Mo. We are so grateful to have you in that presentation. That was brilliant and that was very insightful. Let's give Mo a round of applause, everyone. If you can unmute and clap for her. Well done, Mo. Well done, Mo. Yeah. So
Well done, Mo. Thank you.
Well done.
That's great.
Thank you.
Thank you.
Thank you so much.
Thanks so much, Auntie Mo.
Thank you. So we actually have so far we just have one question.
Okay.
And the question here says, what is space material?
Sorry?
What is space material? So I would simply guess it's what is the material that is being used to make a space shuttle? That's what I think this individual might be.
Space shuttle. So a space shuttle has different parts of it, but it's mainly metal. But in terms of, there's the inner part of the space shuttle, the engine. That's where physics comes in, and where combustion and how you need enough force for it to go up into space. So essentially, the body would be made from a very lightweight metal, so it's light enough to actually go up into space. Okay. I think I saw another question earlier on that said, was it the, okay, no, that was a question of chemistry, physics, and biology.
All right, so that is actually all the questions we have. Is there any other question? If you could unmute your mic and just ask quickly. Okay, there's one from Cornelia. It says, what materials were created in space that does not exist on Earth?
That's a very fantastic question. And Cornelia, you know what we're going to do? We're going to work together because you sound very innovative. So we will work together, and I'm guessing you want to do research and development so we can work together and we can find these materials that were created in space that don't exist on Earth, because you never know, we might want to use it to do many more things on Earth.
Thank you so much, Ajibola, for your question. That was the first question for Ajibola, and then the second one from Cornelia. Thank you so much for your questions, and we want to say a very big thank you to Mo for this wonderful presentation. I'm sure we've all learned new things, and that's what we always do here at AFB Next Gen. We're always here to learn new things about science, technology, engineering, and mathematics. So we will see you in the next 2 weeks.
Rena, can we ask the parents to follow us on social media? I had a thing on there earlier.
All right, we will.
I have one question.
Okay, please go ahead, speak.
I didn't catch what was needed to make the face shield. Sorry, I didn't catch what was needed to make the face shield. So can you say it one more time?
Can you unmute yourself, Mo?
To make the face shield, you have your sponge. So I'll do a quick one. You have your stickers. You have your hole puncher. Okay. So to make the hole, you have your sponge. You have your double-sided tape where you're going to stick your sponge to at the top of the mask. And you have your hair scissors and you have your elastic cord. So remember what this is? These are polymers. So you have your scissors, your elastic cord, and you have your plastic shield. So big enough to cover your face. You can find that anywhere. Okay.
All right.
Thanks.
All right then.
Thank you very much, Mo, for answering that question. All right. So we'll just quickly ask that parents kindly follow us on social media. We have our websites, AFB UK website and the AFB Scotland website, which you can visit at afb.org.uk. And then you can also interact with us on Twitter as well as Instagram and Facebook. So just look for AFB Scotland or AFB UK, and you'll be able to find us either on Twitter, Instagram, or Facebook. So it's been nice having you all here, and we're so pleased, so glad that we had Mo speaking to us on this very insightful and wonderful topic. So from all of us here at AFB UK Scotland, we just want to say have a lovely weekend and have a wonderful week ahead. Thank you for joining us, and see you in 2 weeks' time when we will be discussing computer coding. Bye.